2022, because our first lecture, it concerned 2021. Now we are come to 2022. And it's my great pleasure to announce Professor Adam Jakubowski. Professor Adam Jakubowski was graduated from Nicolaus Copernicus University in 1978, got PhD in 83, habilitation 92, professor title in 98. From 1999 up to 2005, he served as a Dean of Faculty of Mathematics and Computer Science at Nicolaus Copernicus University. He also served in the State Committee for Scientific Research. His research deals mainly with limit theorems of probability theory and static processes, in particular limit theorems of stochastic integrals, stability systems for stochastic differential equations, functional convergence, including non-metric topologies on functional spaces, limit theorems for sums of dependent random variables, including heavy-tailed random variables, and stable and generalized Poisson limits. Limit theorems for order statistics of dependent random variables. Recent interest concerns also digital image processing, in particular image denoising and image segmentation. Professor Jakubowski obtained the Bernoulli book, The Symbol of Presidency of the Bernoulli Society for Mathematical Sciences, on September 9, 2021. The lecture of Professor Adam Jakubowski is Probability on Submetric Spaces. Please, and here's your diploma, as well as a book on Professor Lasoty.
Thank you.
Thank you. And the floor is yours.
Thank you. I would like to thank the jury for appointing me to deliver 15 Lasoty lectures. It's a great honor for me, but also a dilemma, because I was not lucky enough to meet Professor Lasoty in person. Also, my research is practically disjoint with Professor Lasoty's work. In this situation, I decided to tell you a story about one particular device that already proved to be useful in stochastic partial differential equations. So, in area where one can think about some correspondence to Professor Lasoty's work. I will start with some information, which is my personal, in some sense, information. Some publication. The publication is quite old. This is 97. This paper was cited 179 citations. What is interesting in this number is that since 2010, there are most of citations. In 21st, 40 citations. And the picture from Google Scholar is the following. Of course, I realize 40 citations is not 40,000 citations. But on the other hand, this is mathematics, and the topic is accessible not to all people, I mean. So this is quite a successful publication, especially that any citation is a true citation. It's a citation of a particular reference to a particular result that is used as a tool in this paper. And why 2010 was such important for this development? In this paper, in this year, a paper by Martin Andrzeja was published. It is in Electronic Journal of Probability. He, in fact, collaborated with Brzeźniak at the same time, But simple, in this paper, a proper application of the almost sure Skorokhod representation in non-metric spaces was given. So the equation was, according to the title, some wave equation nonlinear with Gaussian, Wiener noise in some sense. It is not important. We will not solve this example, but I will try to illustrate what was the approach presented in this paper. He considered a sequence of solutions that was supposed to approximate the solution. This sequence was two-dimensional, I mean two coordinates, in a sense that this was a derivative in time. And this pair of stochastic processes, it was possible to prove that this sequence of stochastic processes with values in two-dimensional case is in this space uniformly tight as stochastic processes. Here we have a okay, those are standard, in a sense, spaces for such considerations, but the novelty was that it was C with weak topology, weak mappings from R plus to those spaces. And they are non-metric. They are non-metric, so the usual tools were inaccessible, and the idea was to use exactly the almost sure Skorokhod representation from the previously mentioned paper to pass to a subsequence that admits Skorokhod representation. That means random variables on 0, 1, such that the distribution of this par nk for nk indices is like yk. And we have a limit almost everywhere, of course, in this space. So you can imagine it's quite complicated object. We have 2 omega, we have 2 trajectories in some spaces, and so on and so on. But so on some probability space, this sequence was redefined to have the almost sure convergence. And then it was enough to show that this limit is a solution of the problem. Of course, this is a solution weak in distributional sense, that on some probability space there is a solution with the same coordinates. And this is what I mentioned before, that a similar computation or idea was applied in the paper by Brzeźniak and Andrzeja. So they work together in a sense. What is here important when we see such reasoning is that it does not solve everything, but such passing to a almost surely convergent sequence usually reduces, allows you to use deterministic methods to some part, and still usually there is some probabilistic. So it is not a universal tool that solves everything, but it allows reducing the problem to the proper probabilistic problems, or at least avoid many steps to get some conclusion of this type. So a useful tool, and it was possible to see in the citation record of the paper that then many people consecutively were discovering this method, and in this number of citations, there is no my citation, no my friends. It's just all over the world. It's spreading among this community working with stochastic partial differential equations of this type. Let me remind the story. So the story will be exactly about this almost sure Skorokhod representation in non-metric spaces, and I would like to give you some theory behind this. Of course, to formulate the result to make it precise mathematical result, and then to formulate the theory behind that, which, of course, that opens some research, especially should be important for people in Poland, because this, in fact, will transmit the whole power of the metric theory for Polish spaces that we use, we know, to submetric space. So the original Skorokhod representation in seminal paper by Skorokhod from 1956 says that if we have a sequence of random elements with values in a separable and complete metric space, then if the sequence is convergent in distribution, that means we have here the standard definition, of course not very useful, but the definition of the convergence in distribution in metric spaces, there exists a probability space and random elements defined on this common probability space, with values in this space X such that the distributions are the same, and we have almost sure convergence. So this is, in fact, one of very first results on coupling. That means we take property. Of course, not very useful in case, for example, when we have a lot of structure, like sums of independent random variables and so on. So this is not very useful. On the other hand, it demonstrates, it can simplify our reasonings when we deal with complicated spaces, with complicated topological structure. In fact, in this original Skorokhod representation, as the space can be taken standard probability space, one has to say that at the moment we know more. We know more about Polish spaces. We will say that some family of tight probability measures. The whole theory here is about tight. I will not go into problems of measurability, non-separability, and so on. Probability measures are tight. On a topological space, such a family is simultaneously parametrized or simultaneously Skorokhod parametrized if there is a probability space and a map. To each probability measure, we can assign a map on this omega fp with values in the given space, and such that the law of psi mu is mu, of psi mu is mu, and we have almost sure convergence whenever mu n weakly converges to mu 0. So this looks complicated, but this says standard probability space is in fact rich enough to deal with any metric Polish space. On Polish spaces, such a simultaneous parameterization were obtained by Blackwell and Dobbins, and they gave a sketch of the proof, in fact, and they used as omega the square with Lebesgue measure, and Fernik gave a complete detailed proof of this fact for the interval. This Fernik proof is quite instructive. It is maybe considered as interesting complement to this theory that in the paper that will be quoted at least once more, here Bogachev and Kolesnikov in Theory of Probability and Applications show that this kind of parametrization can be obtained from one-dimensional case, which is very easy and well known. It's just inverting the distribution function. Using advanced tools of general topology, Miliutin lemma, Michael selection theorem, and so on. So I can encourage you just to have a look at this paper, which is, in my opinion, quite interesting, to see about the connections of general tools and such a particular topic. What is in non-metric spaces? Because this was the situation on Polish spaces. Let us consider some topological space, quite arbitrary. Our only assumption is that on this space there exists a countable family of continuous functions separating points in X. If such a situation takes place, we say that this space has the property CCSP, countable continuous separation points. Oh, it's okay, it does not matter, but it's just abbreviation for our assumption. Let us, is just to have the formal definition of uniform taut tightness. let us recall that a family of probability measures on a also arbitrary topological space is called uniformly tau tight if for every epsilon there is a compact set, not relatively compact set, such that those measures are on this compact set concentrated with, in fact, exactness 1 minus epsilon here, but in fact on compacts uniformly concentrated with arbitrary exactness. Then, using the terminology of Bogachev and Kolesnikov introduced in the previous paper, we can say that this above-mentioned result has the following form. We have the only assumption on this topological space. This is really weak assumption. For every uniformly tau-tight family of probability measures, there exists a simultaneous weak Skorokhod parametrization. What does it mean weak here? That in each subsequence, we can find the further subsequence with Skorokhod representation. So this is a form that is sufficient for all those considerations, because it's a matter of existence of some representation to get the result. So this was the result, and of course, this has some implications. Of course, in itself it is interesting, but the first implication can be the following: Skorokhod representation for subsequences. When we have this assumption on CCSP, if xn converges in distribution and this sequence is uniformly tight, then every subsequence contains a further subsequence that admits a Skorokhod representation. So again, this is imperfect form. So everybody at some stage who looked at this result was complaining. Roughly speaking, it's not perfect. It's not representation for the whole sequence. It's only representation for subsequence. Yeah. But exactly in this paper, quoted already paper by Bogachev and Kolesnikov, they constructed an example, showed that in general it is impossible to construct a representation for the whole sequence. Of course, they used a special space and they constructed a given special sequence that took values in the space of finite sequences in R infinity, but equipped with topology of the inductive limit, so the convergence is in finite dimensional subspaces, yeah, mainly. So it's not natural convergence. So this counterexample shows that in general, this is the only available result, that this representation for subsequences is a kind of course, law of nature. That means it cannot be improved in general. One remark for the future important, the additional assumption that we have and the sequence is uniformly tight is of course essential, because there are many spaces which are not Prokhorov. That means where relative compactness is not equivalent to uniform tightness. And here the central example for such pathology was detected already, how much? Long time ago, 57 or something like that years. Fernik gave an example of a sequence with values in a separable Hilbert space with the weak topology. So it's really, by separability, this is really clearly a space with this CCSP property. In this example, he showed that it is possible to construct a sequence that is convergent in distribution with respect to this weak topology. But for every R, those random elements live outside of the sphere R. So no subsequence of this xn is uniformly weakly tight, because tightness is concentration on, in fact, bounded, compact in weak topology, so bounded sets in Hilbert space. And those elements live in fact outside of R, outside of any ball in Hilbert space. So no subsequence is uniformly tight, and of course no subsequence of this sequence admits a Skorokhod representation, because if we think about Skorokhod representation and we have a weak convergence along for given omega, small omega, then this sequence is bounded in norm. Being weakly convergent, that means it lives, it belongs to some ball, and we can increase the balls, and we'll see its tightness. It must be tight. So it is in fact, well, it demonstrates the different world. On the other hand, in my opinion, it shows that it is useless for application purposes. On the other hand, of course, if we try to check the assumptions of the previous corollary, and if we have a convergence in distribution and tightness, which tightness, look, it means, uniform tightness means that those elements live inside, with high probability, live inside balls of R, of radius R, while here they live outside. Then, in every subsequence, one can find the further subsequence and the sequence of random elements. That means the Skorokhod representation for this subsequence. So I will write down the properties. First, this is the Skorokhod representation, so the distributions are the same. And for almost all omega and every h. So we have the convergence in given omega. This is the definition of the weak convergence. This means we have uncountable many conditions. So this shows that it is not, this result is not just applications of some diagonal procedure and so on that we can reduce by countable number of conditions. No, this is a real look into the structure of the convergence. So here we have some regularization. For every h, we have a convergence of those random variables. But this holds only for almost all omega. Of course, I illustrated this result with some simplest context. And the question is this theorem only a useful tool, or this is a component of a more general theory? And this is the problem I would like to address during this lecture. In fact, the way to generalize the spaces with CCSP property is to go to submetric spaces. Suppose we are given a topological space with this CCSP property. That means we have a sequence, we order this family, a sequence of continuous functions. Then, of course, we can construct a metric. In standard way, in many ways, we can construct such a metric, which is well defined. And of course, it's a metric because the family separates points. This function identifies points. This is the key property. So this is a continuous matrix on X. And because of the continuity, balls are open and so on, but they are included into the original topology tau. Of course, in general, this metric topology is strictly contained in there. Otherwise, we have a metrizability, so we have a metric, basically, space. So this is a reason to have the following definition. A topological space X tau is called submetric if tau contains a metric topology tau m. So topology generated by some metric. And why the name submetric? Well, this is quite intuitive. At the top of the topology, there is some weaker metric topology. So this probably was used as intuition in this article. where this is the only place I found the name submetric in this context, and no properties, in fact. And I would like to convince you that the submetric spaces are really the spaces we should like as probabilities, because it's quite regular. Behavior is quite nice. It is not that we need some hundred of assumptions and so on to get good properties. No, they are good by themselves. So first, of course, this result, this is the justification for useful, because we have exactly simultaneous weak Skorokhod parametrization. It should be so. The previously mentioned result on the Skorokhod representation in non-metric spaces is valid in submetric spaces. I recall we deal with probabilities with random elements or with probability measures which are tight. So this is the important thing. Of course, in general, this is not true. And now we can go to say why it is interesting. Well, for example, take a submetric space and take a matrix D, which does exist by the definition of submetric space. We can say that D is compatible with tau. Take any compact set. We have this is the basic property, the core property of compact spaces, that the compact topology is the minimal one. So it means that because by definition, tau D is weaker than tau, so they have to coincide on K. One conclusion from that is that compact sets are metrizable, because tau compact sets are also compacts in metric topology, so no problem. This is a crucial assumption in most of the papers, former papers on weak convergence. The other thing is that all metrics, in fact, are equivalent on compact sets. Because if we take another matrix on X, which is compatible with tau, so D and delta must be equivalent, which says exactly this is, because the topologies are the same, and metric topologies are defined by weakly convergence, by convergent sequences. So we have such a crucial property. So on compacts, all compatible metrics are equivalent. So this is the reason we do not mention the particular metric in the definition of the symmetric space, because it's a property, topological property. There is a matrix which is weaker than the original topology, but it does not matter which one we take for our considerations. The other story is how to define random elements with values in submetric space. Okay, the standard definition would be, we should deserve that the preimages of any open set are events, yeah? So this is the standard assumption, usually when we consider a mapping into topological space. This is, of course, equivalent that preimages of Borel sets are events. But we really, such a space can have a complicated structure. We do not know. In Polish spaces, we know what does it mean, Borel space. We do not have representation and a representation, but we know very well properties. In general, we know not much about Borel spaces in T. And we do not need them. Take capital K or script K, a family of tau compact sets, and suppose that only preimages of compact sets are included in F, and that the distribution of that is tau tight. Let us observe that for definition of this fact, to have this fact established, we need only this. Yeah? That's enough. Then, of course, the preimage of the sigma algebra generated by K by compact sets is in F, but we know more. Remember that the distribution is tight. So if we consider family of sets of subsets of X such that they trace on each compact sets belong to the sigma algebra, then of course this is a sigma algebra and Borel sets are in this sigma algebra contained. So, and in fact, if of course we know that the law of X is tight, then in fact the preimage of any set from this sigma algebra R tau is contained in the completion of the sigma algebra with respect to the probability. So there is no problem with writing metrics and so on, nothing like that. All sets of interests are measurable for us. So this can be calculated. We can use this information. So now we can define the space, submetric space. We can distinguish the family of compact subsets of K, of X. The space L0, playing the role of well-known space L0 in case of metric space. It consists of maps, which are first, this is the minimal measurement condition, and second, the law is tight. So by this result, we know we can write down any probability, any integral we want in this space. And we can introduce a natural. In several places, I will use the name natural. And first, it is natural by my feelings, and then there are some facts that I will list in a moment showing that this is really natural convergence. Take a submetric space with compatible matrix tau and a sequence. Suppose that this sequence is convergent in probability with respect to the metric D, compatible metric D, and is uniformly tau tight. Of course, I should recall that this is the definition of the convergence in probability. This is a standard fact, and of course we can write several substitutes for this fact, but for us it is important that there is a convergence in probability with respect to the metric D and uniform tightness. If we take another matrix compatible with D, then we have again convergence in probability with respect to this new, another matrix. So this means this type of convergence we had here does not depend on particular metrics. So again, we have independence of the metrics. So it's quite nice in a sense. And therefore, we can define a natural convergence, which says that if we need for this convergence, and this convergence will be called in the sense of p tau, which is p is involved, both p and tau is involved here, and we will write this way, if xn is uniformly tau tight and xn converges in probability in the metric D. By this lemma, we know here any metric is suitable for this definition. This reminds, such thing reminds some considerations in functional analysis, so-called mixed topologies. Some were considered quite often in 50s by Aleksievich and Viveger and some other people, where we have a convergence in one topology and boundedness in some other topology. But those considerations were related to linear spaces, linear spaces. They were quite, well, interesting in the sense that it was development of some classical and some tool that was useful in some considerations. Here we have also convergence in well-known, but of course this is not a linear, no, it's just the arbitrary space, and boundedness in the sense, and compactness, in fact, uniformly tau tight. So we have, again, natural convergence in this space. And now it's time to define the natural topology on this space. It is the sequential topology generated by this convergence. What does it mean, sequential topology? Because we all are used to using metric topologies. So this is exactly the same philosophy. Recall that a subset is closed in this natural topology if it contains limits of all sequences which are convergent in the sense p tau. And of course, the sequence should be a sequence of elements of F. So standard definition, closeness, like in metric spaces. This is the sequential topology. Why do we expect that the topology should be sequential? We shall return in a moment to this question. Now, let us notice first that this convergence, this type of convergence in metric spaces, in topologies generated by metrics, is equivalent to this convergence, to the usual convergence in probability. And this is not completely trivial, because what we have to prove is that the sequence converging in probability of tight elements is tight, uniformly tight. And this is essentially Lecam's theorem, solid theorem from the basic theory for metric spaces. So it's not quite trivial fact. So in the case of metric, in the metric case, the theory of these spaces, these spaces reduces to the standard theory. But of course, we have to remember, we always deal with elements with tight laws. And the final remark, before we go to the justification why sequential is natural, is about those spaces. This topology here is a submetric space, because we can, of course, given compatible metric, we can consider the metric on random elements, which correspond to convergence in probability. So this is a metric convergence on this space, which is evidently weaker than the original topology, this p-tau topology. So this means with such a formalism, such a space is a submetric space. So we are still remain in the same formalism. And it's time to jump to list some useful properties of submetric spaces. Take a submetric space, and in this submetric space, let us consider the topology, the sequential topology generated by tau. That means we add to tau closed sets, also sets which are tau S closed. That means such sets as in the metric case that contain limits of all convergent elements of the elements. So this is standard definition, and of course we know that tau S closed set, this is a definition of topology. So we have some topology tau S, and in Hausdorff spaces we have that tau is weaker than tau S. It's clear, but it is important here. In the submetric case, we can prove more. Then the topology tau S is the finest topology with the same compact set as topology tau. So it's the finest topology, but the compact sets are preserved. So in particular, if we have a uniformly tau tight family of random elements, then it is automatically uniformly tau S tight. It is interesting because then it means if we have some tool like our theory of representation, there are more functions which are sequentially continuous than only continuous. So it is given uniform tightness, we have automatically uniform tightness, and so relative compactness for stronger topology in sequential way. And there are some other interesting properties. A subset of a submetric space is compact even only if it is sequentially compact. It's really, we do not consider this fact that the compacts are metrizable. It's just sequential compactness. It's sequential. That means in every subsequence we can find a further subsequence converging to this element of this set. So it's quite. This is exactly the compactness we like from metric case. Another property, in submetric space, the closure of a relatively compact set there is a difference between sequential and relative compactness. Relative compactness says in each subsequence we can find a subsequence converging somewhere, not exactly, not necessarily to the limit belonging to this space, to this set. So the closure of relatively compact set coincides with the metric closure and consists of limits of convergent sequences, sorry for this, but need not be compact. And this is a phenomenon known from irregular spaces, when a space is not regular, so such things can happen. But there are ways to overcome this difficulty when we assume something another topology, natural topology. But once again, we have to concentrate on our convergence in law. Commonly, this is, I recall the definition already written here. This is the commonly accepted definition. Convergence in law says that we have a convergence of expectations for every bounded and tau continuous function. Bounded and tau continuous function. The equivalent definition is, of course, when we pass from random elements to their distribution, that we have a convergence of integrals. In other way, if we consider some suitable Banach spaces, then this means that this is a star-weak convergence of laws. So convergence in law of random elements, this is the common practice, is identified with star-weak convergence of their law. This is, of course, completely justified. It's really fruitful approach, but in metric spaces. The Fernic's example shows that in non-metric spaces, this is no longer true. We can get really weak convergence. And of course, this might be interesting to mathematicians. I'm sorry to tell this, but of course, then this is a field for research that in every space we can look for results. But Fernic did it in some spaces, and it seems that the conditions obtained are not easy. To check, and of course, from the point of view applications where people, like in the stochastic partial differential equations, they need some tool and not consideration about general character and so on. So this seems to be a wrong direction. So the conclusion of this side is that weak star convergence of distribution is too weak for purposes of at least some applications. And in this part of the lecture, I would like to define a stronger type of convergence in law of random elements. This new notion will coincide with the standard notion on metric spaces and spaces of distributions, because in some spaces, non-metric spaces, it is the same. In the frames of this new formalism, the whole power of methods of metric theory is preserved. I read this sentence, but this is really the essence. Everybody who knows how to deal with weak convergence of probability measures on metric spaces can do that as well in submetric spaces. Because we have a Prokhorov theorem, we have almost sure Skorokhod representation, and they function the same way. This topology will be finest in a natural sense, and I will provide a sense, showing that this is really the finest topology. And then a remark is that even in the metric case, the new formalism brings a better understanding of some results. For example, in the case of converse Prokhorov theorem. Converse Prokhorov theorem in this framework is, in many cases, we don't need to check Polish, that space is Polish and so on. It depends mainly on the shape of compact sets. On the shape of compact sets, it appears. In Polish spaces, we have special shape, totally bounded, closed. Yeah, this is the characterization of the compactness in Polish spaces. But there are other spaces where for example, in the Hilbert space with weak topology, this is the somewhat different, easier to obtain. Compactness is easier to obtain. So this brings some new light, and this is, this is my personal satisfaction, because when I submitted the paper on the Skorochod representation, I've got several reviews, and one of them stated, well, the title of the paper was In Non-Metric Spaces. So the paper was rejected because it does not bring any new information on metric spaces. Sometimes when you are young, this could be discouraging. Now I have some, of course, distant satisfaction that, well, even in the metric case, it brings new information. And, well, the characterization of the weak convergence on metric spaces is the starting point for our definition of our new secret topology. Take a metric space, the sequential topology, that means the topology generated according to our recipe, from star weak convergence of laws is the finest topology. So the standard weak convergence is the finest topology for which every map, here we have a random element, and we take it's this law, which is the element of tight laws. Such a map should be continuous, where, of course, this depends on the topology here. This topology is equipped with the metric topology of the convergence improbability. So this time I use another definition, but also equivalent definition of the convergence improbability. So we have a standard starting point characterization. It's not completely obvious because in separable metric spaces only it is necessary a bit to work, but still we have such a characterization for metric spaces. So now it's obvious that we define our special natural topology on the space of distributions in the following way. Take a submetric space. There exists some convergence which I put, it is stronger convergence in general than the weak convergence. So there are three bars on this space such that the sequential topology generated by this special convergence is the finest topology for which every map previously considered random element to the distribution is continuous, where this space is equipped with the sequential submetric topology generated by this convergence. So that means we equip this space with the introduced natural topology. So, okay, it's, and the statement is that in particular, this is if our space is a metric space, then both topologies coincide on this space. So this is complete generalization. And of course, the question is, this is the, we introduce some convergence, and we have always a question, we introduce some new notion, can we work with it? So the both answers are, in a sense, given precisely. This stronger convergence if on some probability space there is a Skorochod representation. Then, of course, one delicate point is that given such a convergence, it is not topological convergence. That means this is so-called L convergence if you go to the theory of sequential spaces. But there is a paper by Kisinski, also Bulic. Sorry, I have a good memory. But it is unimportant. Let us use the Kisinski's recipe. Given some convergence, we defined the sequential topology. But the convergence in the sequential topology need not be the original convergence. Can be weak, it may happen, it is weaker. So this recipe says then we have the topological convergence if and only if in every subsequence one can find a further subsequence with the Skorochod representation. So the jumping from convergence to star is described by something that I call Kisinski's recipe. Well, it follows that our opening theorem is in fact a theorem on relative compactness in this topology. Because it says in each subsequence we can find the farthest subsequence this way convergent. Yeah? So it's exactly the theorem about, it's a strong form of Prokhorov theorem for this topology. And one remark, the idea of this convergence is not new. It goes to the paper, and you see this long title published in the Probability Theory, National Academy of Sciences, Ukraine, Kiev. So it's an illustration of the difficult transition time in Ukraine, in a sense. Because the paper was submitted in '94 to the volume with title on, Skorohod's Ideas in Probability Theory. It seemed to be a good place to locate it, because they claimed, the people that invited articles claimed that they would publish such articles in some Western. They had VSP or something like that, some standard publisher in the West. So there was a chance, not a guarantee, but there was a chance to get it published somewhere that is a place accessible. But then, you see, there was a 6 years of nothing, and finally they published this, but in the local publisher. So in fact, this paper was in a sense lost. No, but well, it happens in such a time where situation is difficult. So this is a reason to say this topology, this idea was known. What is really new during this lecture is the formalism of the natural topology on the random elements, the natural topology convergence, and so on. So this is the really something new. And now it's time for, okay, not yet. Completing the picture is that we can prove, simple, I will do prove that the laws with this topology is a submetric space, because given a metric here, we can define a Prokhorov's metric. So the Prokhorov's metric with respect to some metric weaker than tau is, of course, generates metric topology which is weaker than the, surely with that, because this is the strongest topology on this space. So we have submetric space also in for distributions in general random measures. So for example, if somebody wants to consider conditional distributions or random measures on submetric spaces, they are random elements in submetric space. So it's really the reason for completing the picture. And now is this genesis. I am not very original in placing genesis at the end of the talk. We knew from Microsoft Windows that to leave the system was necessary for a long time to press the start button. Yeah? So this is the reason to put genesis at the end of the talk. And what was the genesis for all those considerations? The theorem on the Skorohod representation in the metric spaces and this topology were invented to create a formalism for using some special topology S that I introduced on the space D01, and that was some kind of satisfactory solution to some standing problem without names, but it was a kind of challenge. That the challenger was Tom Kurtz, so it was not bad a competitor in a sense. And this paper was published 3 years later. I would mention here, this was the second volume of electronic journal of probability. So at the very beginning, still Chris Burzy was the editor. We exchanged letters, and he accepted this paper. This is well, for me, of course, it is a quite interesting topology. What is here important that it is a sequential topology. This motif was used several times here, and still it is not known whether it's completely regular or even regular. It is a topology where the addition is sequentially continuous, but it does not mean it is continuous, so we don't know whether this is, for example, a linear topology. But, okay, there are so many secrets. In 94, no machinery existed to deal with. There was only ready theory for completely regular topological spaces. That was the reason to develop the whole machinery. And with this framework presented here, it was, of course, possible to go further. And this S topology was used in the future, and of course the presentation of this topology would require another lecture, so I would not present it here, but I would like to turn your attention to quite fresh and, in my opinion, very interesting example of how to use the notion of S topology given in the paper, quite fresh also, published recently. And this is, at the moment, the most general martingale optimal transport duality result obtained using tools taken from this topology. I must say also that Matti Kiski also contributed to understanding of such results. And finally, once again, use submetric topologies. This is the call at the end. Some people did it and were able to obtain interesting results, including myself. Thank you for your attention.
So now we have time for questions and comments. So, okay, Ryszard.
That the space of distribution, the D prime, is an example of some new notion, yes? So something like that it was in your talk. So it means that the space of distribution D prime is not submetric space, yes?
Yeah, it is. It is submetric. It is submetric. You take any countable family of sample functions, and you get from D, and you get submetric property. It is not exactly what you said. Space D prime and S prime was example of the standard, that the standard notion of weak convergence works on those space, and the new one coincides on those space with standard convergence in distribution. So it is example of a submetric space. It is example of submetric space. That's right. But this new form, this formalism does not bring any essentially new for this space. Yeah.
Okay, maybe another comment is my comment concerning applicability of this result. As I understand, very often we would like to solve stochastic PDEs, and then we have a weak sense solution in a weak sense, and we can have this for regular coefficients, and then when we don't want to have a regular coefficients, then perhaps then we use Skorohod embed, Skorohod representation result. Is it true? And
no, you need some continuity. Remember that if you replace the coefficients which are irregular with regular, then you are in problems. Yeah, no, but of course this is the idea. So this is not so automatic. I mean, but if you look at those papers, well, in some papers I didn't mention them. I started from Lithium 2, but some recent papers uses products of 6 spaces. That means they consider stochastic processes with values with some components in 6 spaces, and they get stochastic representation good for all those coordinates. I mean, so they can involve many things. But this is not so automatic. You need, to apply your reasoning, you need continuity of results, continuity of coefficients in a sense. Here, no, but in most cases, there are, if you assume some Lipschitz continuity, then of course you are done, yeah.
Yes,
but then you have some other tools to do that.
But then another question, because your fundamental assumption was this countable separability, assumption that we have a countable family of continuous functions that separate points. But there are many spaces in which you don't have this. So, do you have any idea what to do to consider, let's say, special relation, quotient spaces?
If you take Hilbert space of the power C, I mean that with number of dimensions C, then you don't have this CC as P property, but it is still a metric space. So, but of course, then if you consider probability distribution on such high-dimensional, really high-dimensional Hilbert space, and you consider tight measures, they are living in proper spaces on separable Hilbert spaces and so on. If we have tightness, in such spaces. So it is not true that it is very difficult that there are really some spaces without this countable separability property. Of course, if you take supremum over uncountable set like in this, but then usually you don't have tight laws and so on. You enter the whole area of external integrals and the Hoffmann-Jorgensen tools and so on. It is of course important, difficult for young people. Young people can have problems. I was a reviewer of some result of this type, and the young guy, the author, was not, of course, manipulating with external expectation and so on, but took the expectation of the uncountable sum of almost surely equal to zero random variable as a sum of zeros. So that was a mistake. It's difficult, I mean, and I think this is in most cases we have the good properties that we can apply this formalism. I would like to pose open question at the end without talk. Can I?
Okay.
Okay, so this is this space of random elements corresponds to usual space of, in metric case, corresponds to the usual space of with convergence in probability. Yeah? When we have a sequence convergent in probability, we can find a further subsequence convergent almost surely. We know that very well. But can we find such a simplification in this space? It's the counterexample provided by Bogachev and Kolesnikov shows that even if we have almost sure a convergence in the matrix and uniform tightness, then it does not imply almost sure a convergence in general, in topology. Yeah? So it's simple. One would need a method of reduction of like in the case of convergence in probability to convergence almost sure in this more general space of random elements in submetric space. I have no idea. At the moment, the only way of reduction is that you have a convergence, then you have some subsequence with Skorokhod representation, almost surely convergent, but on some other space. So this is not clear, yeah. So this would be a kind of complement to this theory, making the more satisfactory in a sense.
Okay, any other questions or comments? Do we have? Okay.
It's perhaps not so important, but the topology, the submetric topology in this given space can be also defined using the so-called diagonal mapping. Whenever we have a continuous family, a countable family of continuous functions which distinguish points in that sense which you defined, then we have also one-to-one continuous correspondence of the given space to a subspace of the Hilbert cube. So it automatically gives a topology in the given space which is weaker than the Hilbert topology, I mean the subspace. Some subspace of the Hilbert cube. And moreover, it seems to me that it also follows that the Borel structures on both spaces are the same. It is just Borel isomorphic, that submetric space, with a subspace of the it is just equivalent in Borel isomorphic to a Polish space, because every subspace of the Hilbert space is a Polish space also. So it is another way
every subspace of a Hilbert space is Polish space? No.
Yes, because it is metric, so it has a countable base, so every subspace also have a countable base, so it is separable. Oh, sorry, it have to be closed. So it have to be closed. So this is only one. Or at least it should be Borel. It's also.
Yes, with Borel, I agree, but
yes, it is Borel.
But not that every.
But it seems to me that it should be Borel because the functions were continuous, so they preserve Borelness. Yes.
Okay, you think in category of the CCP SP property, yeah?
Yes.
So it's well, this is in fact embedding of homomorphic. No. Measurable homomorphism into the subspace of R infinity, which is on compacts, homomorphism, and of course the structure of so this was used, this was proved in fact this way. I mean the result was proved exactly this way, so it is not. What I wanted to say here is that we can have properties which are free of the explicit metric here, also of embedding somewhere and so on. It's you recalled me that perhaps exactly something like that was considered in this handbook on topological space.
Yes.
In this handbook,
yes.
And well, perhaps it's my fault. I ignored.
I don't remember that paper.
No, because I was just looking. What is the reason this result is can be interesting for people in applications? Yeah. Formulation is extremely simple. They know most of spaces they consider have this CCSP property, yeah? And we tried to do some theory for submetric spaces, which is clearly more general than the previous case. Well, it's topological. If we have some properties that are not dependent on this particular metric, so this is the well, for me, it was interesting. I mean, while thank you for the context, perhaps I have to look again at this paper. I did not find there information that were helpful for this kind of reasoning. Yeah, so that's the reason I recorded only the name from the. Thank you for.
Okay, we have another question, perhaps. Do you have any questions? Not more? So let's thank our speaker once again. And now it's time to announce that 2022 Lasota lecture celebration is closed, and we are waiting for 2023 celebration next January, I hope, because there's a tradition that January, and hope that we will manage to organize next year. Thank you, everybody. Thank you. Bye-bye.